In this section, we will discuss about the single electron transistor. So we will start with the definition of single electron transistor. A single electron transistor is made from a quantum dot that controls the current from source to drain, one electron at a time. Okay. So this type of transistor is called as single electron transistor. So basically it is made from a quantum dot, or it is the quantum dot is an essential part of it, and that controls the current from source to drain. Okay, when you consider the field of a transistor, we are having three different parts for this field of a transistor, and those are source, drain, and the channel. Okay, and here we will be having a similar kind of structure, but there is a small difference. So if you consider the FET, field of a transistor, so in this case of field of a transistor, we are having source, drain, and so you'll be having one end which is the drain, and then you are having the channel, that is denoted like this, and then you are having the source. This is source, and this is your drain. This is drain. This is source. Okay, like this, and this will be connected to some potential, and you'll be having a gate terminal here. This is your gate. So this will be also, this is connected to voltage like this. Okay. So here also we'll be having this drain, will be having positive end. This is negative, positive and negative like that. So this is the diagram of a field of a transistor. Okay. So here we are having three different parts for this field of a transistor. But in the case of a single electron transistor, it is almost same. But instead of that channel, we will be having the quantum dot. Okay, so here we will be having a quantum dot, and this drain and source part will be separated from this quantum dot with some gap. Okay, so that is the basic difference from the FET that we can have for the case of single electron transistor. That is the difference, and this gate will be connected to this quantum dot through a capacitor. Okay, so we'll be having a capacitor here, and this drain and the source and which are separated from this quantum dot which is at the center. So here instead of the channel we are having quantum dot, and as you know this quantum dot is at all the three dimensions will be less than 100 angstrom. So then only that will form a quantum dot, which means that in x and x, y, z direction we are having the length which is less than 100 angstrom. So such a material we call it as quantum dot. Okay, and this for this quantum dots we will be having discrete energy levels that we already discussed. We will be having different points like this. So we are having discrete energy levels for this. When when you are considering the density of state versus energy, also we get this kind of dots. So basically this quantum dot will give you discrete energy level. So we will be having this kind of energy level structure for these quantum dots. So we are having in the case of single electron transistor, we are having quantum dot instead of a channel in this transistor configuration. And then we are having two tunnel junctions here. Here we are having a tunnel junction. Here also we are having at another tunnel junction. So these two tunnel junctions are in between this drain and quantum dot and source and quantum dot. So basically that will be like this. This is your quantum dot and you will be having drain here and you are having source here and gate here. Okay, and this gate is after gate we are having this capacitor. Okay, so this capacitor, so we are having some gap here basically, gap between this quantum dot and this drain and the quantum dot and source. So this gap is very small and we can have some kind of quantum mechanical tunneling which can happen in between these two, in between this drain and quantum dot, that you might have studied in quantum mechanics. If you are having some barrier like this, and if you are having some particle which is not having that much of energy to overcome this potential barrier, then they will tunnel through this barrier and it can be found at the other side of this barrier. Okay, this kind of quantum mechanical tunneling is possible in this junction also. That's why we are calling this as tunneling junction. Okay, so this is your tunneling junction, and we are having two such junctions in case of single electron transistors. So these are the basic difference. If you are considering FET, then we will be having channel, then that drain region, then we are having source region like this. So this is drain, source, and we are having channel. So we will be having something like PN junction in here. Okay, this is a P-type material, semiconductor material. This is N-type. So we will be having PN junction in between this channel and drain as well as source and channel. But in here we are having a tunneling junction instead of a PN junction. So these are the basic difference between field effect transistor, conventional field effect transistor, and a single electron transistor. Now, if you further consider, so this difference we have already covered. So basically, these single electron transistors are built like a field effect transistor. This is the configuration is almost same, but in set, that is single electron transistor, instead of the semiconductor channel between the source and drain electrodes, there is a quantum dot. That is the basic difference, first difference. And also we are having two tunnel junction in case of set, single electron transistor. Now if you consider the construction of set, how we can make this set. So we are having the quantum dot. Okay, that is nothing but a conductive, acting as a conductive isolate, which means that where we are having this electrons which is passing through. And then we are having this quantum dot which is separated by two thin insulators from both source and drain electrodes that we already discussed. We are having some separation between this drain and source, which means that they are not connected. So we can use some very thin insulators that air itself we can act as insulator here. So any other material you can use. So here we can consider any thin insulator layer between these two. Okay, very thin, so that the quantum mechanical tunneling has to happen. Okay, so that is the first thing that we have to consider. Then we are having these thin insulators, which will act as tunnel barrier between the source to quantum dot and quantum dot to drain, that we already discussed. And the gate is connected to the quantum dot through a capacitor. That also we discussed. We are having a capacitor here, and that this is your gate, and this gate is connected to the quantum dot through a capacitor. And in single electron transistor, electron tunnel in two steps, such as source to the dot. So first the tunneling will happen from drain to, the electron will be flowing from source to drain. So electron will be flowing from source to quantum dot first, then from quantum dot to drain. So this is how electron flows. Current will flow from drain to source. So electron will flow from source to quantum dot first, then from quantum dot to drain. So the tunneling will happen in two steps. Okay, two steps. First step is the tunneling of that electron from source to dot, quantum dot, and then from quantum dot to from dot to drain. Okay, so that is tunneling. Two steps are there for this tunneling. So then only the electron will reach from source to drain. Okay, and then we are having the gate voltage Vg that controls the charge on this capacitor. So all this will make the capacitor. Okay, so basically all this will make the capacitor of this particular quantum dot. We are having, if you are considering some charge here, if this quantum dot is also having charge, then two charges separated by an insulating layer. So that is going to make a capacitor here. Here also we will be having some capacitance, and here we are having the capacitor that is connected to gate. So total capacitor will be a summation of this capacitance, and that will be Cg plus, let's say this is Cd plus this is C source, and this is the total capacitance. Okay, and this Vg will control the charge on this capacitor, this gate voltage. When you connect this to the voltage, then this Vg will, this is your Vg. Vg will control the current flow through this quantum dot. And there are some rules for single electron phenomena to occur. Okay, that I think, okay, we'll discuss that here itself. First one is the Coulomb blockade. Okay, and the second one is it has to overcome the uncertainty or overcoming the uncertainty. So first we'll consider what is this Coulomb blockade. If you are considering this quantum dot, which will be having some charge, so electrons will be there inside this quantum dot, and if you are having some amount of electrons in that quantum dot, then that will produce some potential through this Coulombic interaction. Okay, so we'll be having very high negative repulsive force here, and in such a way that this, if you are providing more electron to this quantum dot, it will not accept that electron, it will repel that electron with some potential. Okay, so basically this kind of a charge distribution will have some potential. Okay, and that potential will always resist an additional electron to enter to this system. And so if you want to add this electron also into this system, then you need to give some additional energy to cross this potential, or to cross that repulsive force. So you have to do some work to reach into this quantum dot, and you had to provide some energy to this electron if you want to get into this quantum dot, if you want to get this electron, if you want to take that electron into the quantum dot, then you had to provide some energy, and that energy should be more than this Coulomb uh, energy. If you are having V, then if you multiply that with this charge, okay, for example, if you are considering electron, then it will be V into E. That much of energy you have to provide for this electron to cross that particular potential field to reach into the quantum, this quantum dot. Okay. So in order to explain that, first we'll consider this working. So as you can see here, to control tunneling, voltage bias is given to the gate electrode. Voltage bias is given to the gate electrode. So we are having some voltage here for the gate. Hope you can see this. That is to control the tunneling process. And a separate voltage bias is given applied to between source and drain electrode for the current direction. Okay, so we are also having some potential applied to this in between this source and drain, and the in such a way that the current will be flowing from drain to source in this direction. Okay, in such a way that we are having some potential applied to this, or some separate voltage bias is given to this drain and in between this drain and source. And when gate bias voltage, when the gate bias voltage must be large to overcome the Coulomb blockade energy, then only the current will flow. So as we discussed, so if you consider the case like if you are having two conductors like this, separated by a very small insulating layer in between that capacity, these two conductors. Okay, so if you consider electron movement from this side to the other plate, second conductor, that is possible through quantum mechanical tunneling. So once this more number of electrons reached on this particular part, this conductor, okay, then it will produce some potential. Okay, we'll be having some, because this is a conductor, this is another conductor, so this will act as a capacitor. Both two conductors are separated by an insulating layer. So there will be an additional electric field which will be generated in between these two plates, and that electric field will repel further movement of electrons. And if you need more electrons to be moved from this plate, first plate, to the second plate, then you need to provide some extra energy. Okay, so that is the same concept that we can apply here also. When you consider the quantum dot, you are having some electrons in this quantum dot. Okay, and these electrons will produce some potential, Coulombic potential, due to these interactions. And if you add more electrons to the system, this system will always try to repel this electron. With how much energy it will do? To calculate that, let us consider this. So let us consider this is the energy. For example, the energy needed to move charge Q inside the quantum dot, that is given by E equal to V into Q. Okay, and this Q is E, that is the electron charge of that particular particle. Here we are considering electrons movement to the quantum dot. So if you need electron to this quantum dot, how much energy you need? That is E equal to V times Q. What is this V? V is the potential produced by this quantum dot. through because of these charges inside this quantum dot. Okay, so if you are providing this much of energy for this electron, that is E into V, that is V is this potential produced by this configuration quantum dot, then only this electron can move into this quantum dot. So that is V into E. Okay, so from that we can say potential V, which is equal to E by E. Now, what is this energy? What is this energy? That energy is the energy required for this electron to cross this potential and to reach this quantum dot. Okay, how much is that energy? That energy will be equal to E square by 2c. This energy is E square by 2c. Okay, that is the Coulomb blockade energy. This much of energy is required for the electron to cross this potential and to reach this quantum dot. The potential. So potential will be equal to, so that will be E square by 2c divided by E, right? B equal E by E. So this is the Coulomb blockade energy. Okay, E equal to E square by 2c is the Coulomb blockade energy. And so we will get E square by 2c by E is the potential. Okay, so from that we can say this is E by 2c. This C is capacitance. So this is the potential that we have to apply on that gate terminal, or we have to apply this voltage. We have with this voltage applied to the quantum dot, an electron can tunnel through the quantum dot if you are applying this much of voltage. Okay. So now let us consider the operations when you apply that much of potential, what will happen. So let us just consider this figure here. Take this. This is same figure which is reduced to somewhat. So this is same figure that we have shown here. We just represent only those junctions here. So we are not going to discuss about gate, source center, gate, drain, all those things. But you have to focus on these junctions. These first tunneling junction, second tunneling junction. Okay, and we also have one capacitor here. So we can reduce this figure again into this form. We are having one capacitor here, another capacitor, that is the tunnel junctions, and then we have additional capacitor here for the gate. And this is the source potential Vs, this is drain potential Vd, and this is gate potential Vg. So as you know, the energy will be, that is the Coulomb blockade, that will be equal to E square by 2c. Okay. So if you increase this capacitance value, or if you change this capacitance value, your E will be different. So initially, when there is no voltage applied on the gate, then your electrons which are present in the source will be having some energy level like this, and the quantum dot will be having energy level which is the empty energy level somewhere here, and the drain side will be having energy level somewhere here. So in source we are having a lot of electrons, but that electrons cannot move to the drain. So this is your source and this is your drain, and this source electrons cannot move to the drain because we do not have any energy state which is in that level. We will be having different energy states here, but they are occupied. Okay, these sorry, these are electrons. So these are occupied energy levels. These are occupied. If they are having, so all these energy levels will be having electrons, but this energy level is free, or this is unoccupied. It is not filled. So this is occupied or filled. This is unoccupied or which is unfilled. Unoccupied. But these electrons cannot jump to this energy level because it is not having that much energy. The energy of this electron is this much in source. So we are having electrons in source. Those electrons are having energy which is less than the energy level of in the quantum dot. So this separation is the Coulombic blockade. That is nothing but E square by 2c. So this electron should have this much of energy to get into this energy level. Okay. So then only it will reach to that energy. Then it can go to the drain side. Otherwise, it can move. It cannot move. Okay. So it has to get this much of energy to cross that Coulombic blockade. This E square by 2c energy. Then it can move. So here, how we can get this electron into this quantum dot. This is the quantum dot, this region, and this is drain. So how we can get this electron into this quantum dot? So in order to get that, we have to provide this much of energy. Okay. So the energy separation from an occupied to an unoccupied state in the quantum dot, that is given by E square by 2c. So if you are, it depends on the energy level of this source. So if the energy level of the source is in this level, then it needs E square by 2c energy to reach into this energy level, which is unoccupied. Okay. So when you consider that case, this can be done by applying an additional potential in the gate terminal. So if you provide some potential in the gate terminal, which is at this point, so it will change this capacitance. Okay, it effectively change the potential of this quantum dot. Okay, and hence it will reduce the energy level to somewhere here. So when Vg is equal to 0, when Vg equal to 0, this energy level will be somewhere here, and the electrons cannot move to this quantum dot because the unoccupied energy level is higher than that of the energy level of this source electrons. And when you increase the gate voltage, then this it will change this potential at this quantum dot, and effectively what is happening here, you are going, when you change this potential, you are going to change this the potential of this quantum dot. Okay, and that effectively reduce this energy of this unoccupied energy level of this electron. So basically this what will happen when you apply, this is Vg equal to 0 condition. When Vg will become which is greater than 0, or we can say which we have to apply negatively. So when Vg is not equal to 0, Vg is not equal to 0, in that case, this energy level will be somewhere here. And the electrons can directly go from source to this unoccupied energy level in quantum dot. And from there, it can directly go to this drain. So when you provide this much of energy, E square by 2c. Okay. So this is the basic principle of the single electron transistor. So when your Vg is equal to 0, the electron cannot move from source to quantum dot because the energy level is the gap between these two energy level is larger, and we need this energy level has to be smaller than this energy level in the source. In order to do that, we have to apply some potential in the gate. When you apply the potential in the gate, then it will reduce the energy level of the quantum dot, and so that the electrons can move to the quantum dot, and from there it will go to the drain side. So the current conduction will happen. So when Vg is equal to 0 here, in this case Vg, when Vg is equal to 0, let us consider Vg equal to 0. So there is no change in this potential here, and the effective capacitance will be equal to C sigma, which is equal to Cg plus Cs plus C drain, right? And so that your energy level will be equal to E square by 2C sigma. So this will be like this energy level. But when you consider an additional potential when Vg is not equal to 0, that this capacitance will increase here, and effectively, so because this is Cg here, Cg plus C plus Cd, so this will increase, that effectively increase Cw, sorry, C sigma, and that will reduce this energy, which means that this energy gap between the unoccupied and occupied energy levels will decrease, and the energy level will become less than that of the energy level or of the source, so that the electron can move to the quantum dot, and then from there it can directly go to the drain side. Okay, so once this electron moved from this quantum dot to the drain, if you are providing that much of potential again for Vg, then again the next electron will move to this level and this process continues. So this is the working how this the single electron transistor works. That is what we have just explained. So again, we will discuss these 3 points. As you can see here, a separate voltage bias is applied between source and drain electrode for the current direction. When gate bias voltage must be larger to overcome the Coulomb blockade energy, the current will flow. The energy need to move charge Q inside the quantum dot, that is given by this equation. And from there we have considered this potential. So this much of potential you have to apply for the Vg, gate voltage. Then only that energy of electron can overcome the Coulomb blockade. So this is the potential that you have to apply on the gate voltage. So now if you consider the gate voltage against average number of isolated electrons, that is the electrons present in quantum dots, then when you apply E by 2C of potential, that is the potential that you have to apply in the case we discussed here, that is the potential you have to apply, minimum potential that you have to apply for Vg terminal, gate terminal, so that the electron can move to the quantum dot. Okay, so if you apply E by 2C, then you can observe only one electron which is moved to the quantum dot. So average number of isolated electrons, that is the number of average number of electrons present in that quantum dot will be 1. If you consider 3E by 2C, then you can get 2 electrons. If you consider 5E by 2C, this is gate voltage, then we'll get 3 electrons and so on. So basically it is a multiplication, odd multiplication of E by 2C that will increase the number of electrons, average number of electrons in the quantum dot. So if you can generalize it is Ne by 2C, where N is equal to 1, 3, 5, 7, and so on. So that we can observe from this particular graph with respect to the number of average number of isolated electrons or electrons in the quantum dot against the gate voltage. Similarly, if you make the bias voltage less than that of the voltage, minimum voltage need to transfer electron from source to drain, that is E by 2C. If the biasing voltage is less than that, in that case we'll get oscillations. Current will be oscillating with respect to this Vg, and that oscillation will be like this. Okay. So for this, this particular variation in current with respect to Vg has to be observed. The biasing voltage has to be less than the minimum voltage that we have played in the uh, gate voltage. Okay. So if the voltage is kept constant, that is the voltage, the bias voltage kept constant below the Coulomb blockade, and then we can have a current which is oscillating with a period of E by Cg, with a period of E by Cg. And these are the Coulomb oscillations. Okay. And that we can represent like this for different E by 2C values. You can see here 1, 3, 5. So this is 1 E by 2C, 3 E by 2C, 5 E by 2C. So we can have some kind of oscillations here for the current. So this is drain to source current, IDS. Okay. So this is how the single electron transistor will work. Yet we have so many limitations for this particular technique or this transistor, because when you consider the fabrication of this single electron transistor suffers many difficulties. For single electron transistor to be used in a large scale production, the following factors must take into account. First of all, it is very important to develop technologies for forming nanoscale quantum dots. That is the first thing that we have to consider when you are making single electron transistor. First of all, we have to make the quantum dots. Okay, so we need technologies to make such quantum dots. It is very expensive. Okay, and then we have to couple this quantum dot through tunneling barrier, and which must be precisely controlled in their size and position. Okay, so we have to make this quantum dot. We need all the technologies for that. Then after making these quantum dots, after having this quantum dot, then we have to have this kind of tunneling junction. We have to connect that with this semiconductor material like this. So when you, so this is already in nanometer. Okay, this is quantum dot less than 100 angstrom. Okay, so this is already in nanoscale, and this also has to be in nanoscale. This also, this side has to be in nanoscale. So then you have to arrange that with a very small gap or small, with a very small insulating layer in between here also. So you have to arrange this quantum dot and the source and drain like this, and their position also very important. They have to be in line. So all these kind of things you have to take care of when you consider to make this kind of transistor in more number. If you are going to make these transistors or produce this kind of transistor in a massive way, large quantity, then you have to consider all these things. Okay, so the size here the size and the alignment or the position of this semiconductor and these quantum dots also very important. Also, there are many damages that also possible. Also, contaminations may be possible while developing these kind of quantum dots and very nanoscale materials. So all such kind of things should be avoided during this large scale production. Okay, so we can write that also here. So there are possibilities. These are the uh, important factors that we have to consider when you make these kind of transistors uh, in large scale. So there are possibilities for damages and contamination. So all these things we have to take care when you make this kind of devices. So all this should be avoided in the fabrication. Okay, this possibility of damages and contaminations, other the possibility of other particles get inside to this content or to these materials. All those things are possible. So all those kind of things has to be or possibilities has to be avoided or it has to be taken care of. And also the technique must have very high reproducibility, and also it has to be controllable. So the technique must be reproducible, or we can say this technique means the device that we are making, that must be reproducible, or we can say this is, we have to consider the technique. When you say it is technique, this must have must have high reproducibility, also, and controllability. Controllability. So this is 12. So it has to be reproduced. If you make one transistor, then the next transistor also should have the same kind of shape and configurations, all those uh, values, size and alignment, all those things. It has to be same. So the technique must have high reproducibility, which means that if you are having some technique to make one particular transistor, that is single electron transistor, next time also it produce the same transistor. So reproducibility is important, and also controllability. We have to control the technique. We should control the technique. It should not be uh, harm. It should not make any harm to the environment or to the people. Okay? We should not be making any such kind of problems to the environment or to the people. So we should control the technology, should be, or the technique, that has to be controllable. Also, it has to be reproducibility, a high reproducibility should be there, so that we can make large number of these kind of transistors. So because of all these difficulties or these conditions, it is difficult to produce that in a very large scale. Okay, we need these all these kind of features, which means that the technology we need technology to make the quantum dots and to align them in the same direction or in the same line, with a very small gap between this semiconductor and the quantum dot, which will make that tunneling junction. All those things we have to take care of. And during this process, there are possibilities for damages and contaminations. Many other materials can involve this in these reactions. And also, while making this kind of device, there are many possibilities of damages because we are dealing with nanoscale. Okay, and also we need high reproducibility for the technique, and also the technique has to be controlled. So these are the factors that we have to take care of when we are producing this kind of uh, transistors in bulk amount, large amount. Besides, there are many advantages for this kind of transistors, single electron transistors. First advantage is it is very fast. This is fast advantages, you can say. Advantages of this fast information transfer. And another advantage we can say it is suitable for high density memory. Suitable for high density memory. And third one is can be used for quantum computers. Use it for quantum computers. And many other advantages also there. We are listing some important of advantages. So then when you consider applications of these single electron transistors, then we can say this is used for mass storage of data. Large amount of data can be stored, and then we can use in sensor technology. Different sensing applications we can use. Then by using this, we can design logic gates by using this transistor as with the other transistor also. Like the other transistor also, we can use this for designing logic gates. Also, this can be used in very sensitive electrometers. So these are some of the applications. There are many other applications also uh, available that you can note down. Already listed this here also. You can say this can be used in quantum computers, and also we can use this in for microwave detection. microwave detection, and so on. Many applications are there. Okay. So this is the basic, some of the basic idea behind this single electron transistor. I hope you understood its working and structure. Also some applications, some of the applications of the same. And I think I missed one here. That is the uncertainty. So it has to overcome the uncertainty. So the uncertainty also is one of the condition. Like blockade, because we have E equal to E square by 2C. That is the energy required to cross at Coulomb blockade, as we discussed. Okay, like this. So this much of energy you need. Okay. So in order to, when you consider this energy, we have another energy which is the thermal energy. Thermal energy, that is nothing but KT. So if you are having at room temperature, if you are having this KT, which is larger, if your KT, that is the thermal energy, if it is larger than this E, then these electrons can directly go to the drain side, from source to drain. Because if this KT is larger than this energy E, let's say this is EC for Coulomb blockade. So if it is larger than this EC, then it can directly go to this T, because these electrons, it was here, but because of this thermal energy, this electron will get additional energy and it can go up, and it will be above this energy, more than this Coulomb blockade. Then the electrons can directly go from here and it will reach into the drain site. So we cannot control that electron. So if you want to control that electron by adjusting the gate voltage, this KT must be less than EC. So this is the condition. KT must be less than EC. So at room temperature, even if you are considering the temperature is there, some temperature, or when you are considering this kind of uh, single electron transistors, the temperature has to be small in such a way that it has to be, it depends on that EC value. It depends on that quantum dot and the material that you are using, and how much the separation tunneling uh, gap. Okay, so all those things will depends on this energy. So we can say if you are considering this kind of condition KT, which is if it is greater than EC, then it will directly, these electrons can directly go to the drain side. So we cannot control that electrons. If you want to control that electron, this KT must be less than EC. Okay, it has to be less than EC. So one way is to achieve this condition is you have to do the experiment at low temperature. Then you can have KT which is less than EC, or your EC has to be much higher. Even if you consider some higher temperature, it has to be less than that of EC. So that is the condition. That's why we need this Coulomb blockade. That is necessary. If you don't have this Coulomb blockade, then you cannot control that electron by adjusting the gate voltage. And second one is the uncertainty. We have to address that also. So what is the condition here when you consider the uncertainty? So basically you are having the equation for uncertainty, that is delta E into delta T which has to be, I think you might know this. Delta E, delta T. Let us consider that as H cross, or H by, can consider it as H by 2. And this time depends on your resistance, right? How it is going to depend on your resistance? Because your resistance is, I will just write it here. So let us consider this as, for simplification, let us consider delta E, delta T is almost equal to H. So it actually, the condition is this has to be greater than or equal to H cross by 2, or you can consider H by 2. So this is the condition. So if it is greater than this value, then we can approximate that as equal to H for the calculation purpose. So this is delta E into delta T is equivalent to H. So delta T is the product of the resistance and capacitor when you consider that time constant RC. So this C is corresponding to the dot, quantum dot, capacitance of quantum dot. And R is for resistance of tunneling, And if you do this calculations, so then it will come delta E will be equal to H by delta T, and that will be equal to H by RC. And this H by R, then this H by R, that has to be, if you consider that symbol here, so this H by R should be less than that of E square by, this is E square by 2C, right? So H by R, if you take E square by 2C will come here. So this will be E square by 2. Now, if you are considering that greater than here, then if for uncertainty, so this will be H by R. That has to be like this. So in that case, so here we are considering the greater than. So in here we are not considering that because of easiness of calculation. Delta E will be equal to H by delta T. Or you can directly take this as greater here, greater than or equal to. If you can take that condition, so this will become greater. So H by R should be less than that of E square by C. E square by C is coming from here. E square by 2C is the energy difference. So that will give you E square by 2. And this will give you, again, if you reduce this R should be greater than, this will be, how much is this? 2H by E square. So this is the condition. The resistance of tunneling must be greater than this value. And that you will get approximately, that value is 25.8 kilo ohm. So this is the condition. These two conditions has to be followed. This must be there. Then only you will get that the single electron tunneling. Okay, so what was the first condition? First condition is E square by 2c. This energy must be greater than kT. Okay. Then second condition is this. R must be greater than single electron transistors. I think I have missed that point here. So that two are here. Rules for single electron phenomena to occur. So these two conditions has to be followed. And all other things we have explained, how it is working, what is the structures and applications of the same. Okay.